Welcome to the ninth lecture in this chapter. In this lecture, we will discuss transactional memory. So lock and unlock functions, the way that we have described, have a problem. So let us first understand what we have described and what is the problem. So let's take a look at this function update balance. So what we do is that if this is the bank account of class account and we want to, let's say, add a certain amount, which is amount. So then we acquire a lock, and let's assume that we have a single lock. So we just acquire a lock and then we read in the account balance. So the code has been written in such a manner that one line of C code translates to one line of assembly code. So what we do is we first read in the balance, which is a memory read operation. Then we add the amount to it. And finally, the updated amount is written back to the account balance. So this requires a load instruction. This requires an add instruction. And the last statement requires a store instruction. And finally, we relinquish the lock, we get rid of the lock. So we do it by an unlock call. So these are the two calls, lock here and unlock here. We enter the critical section, which is this. In this, we update the account. So if you have one lock, then there is no parallelism in the system, because let's say that this is for a huge bank and there are 10,000 customers. So then they cannot operate their accounts in parallel, even though their accounts may not have any dependencies between them. But still, the accounts cannot be updated in parallel, and that is an issue. So we need to have much more parallelism. The only constraint is that we should not have two parallel accesses to the same account. Or let's say that in a more complex scenario, if two accounts are linked, then it may be necessary to lock all the accounts before a single transaction is allowed. But most often, this is not the case. That's the reason when two accounts are disjoint, which means that there is no relationship between them, we should be able to update the accounts in parallel. This is known as disjoint access parallelism. So disjoint access parallelism will give us the parallelism that we seek. In this case, it is just that with a single lock and unlock function, we are not getting it. So now let me show a piece of code which is far more scalable, in the sense that disjoint access parallelism is allowed. It is the same code, but instead of having one global lock address, we have a lock address associated with each account. So we lock that, then we proceed to do the account update, and then we unlock. All right. So we go lock, we proceed with the account update, and then we unlock. And furthermore, we have account specific locks. So this does increase the memory footprint, right? So the storage area of the program, the memory footprint increases. The reason being that previously we had one lock, and now if we have 10,000 accounts, we have 10,000 locks. Nonetheless, this is a very scalable solution. In fact, this is something that is used. But again, there are problems. So the problem is that assume that there are linked accounts, right? So let's say that in different banking systems, we have these joint accounts, and sometimes it is necessary to check one account before actually updating it. So I'll give a simple example. Let's say that there are two accounts A and B, and we want to withdraw some amount from here. Let's say we want to withdraw 100 rupees from here, and we want to transfer it over here. So one thing we need to check is that whether the first account has 100 rupees or not in its balance. And second, we need to check if account B is frozen or not. So many times what happens is, because of different law and order reasons, account B may be frozen. If it's frozen, we can't transfer any money to it. So what we would need to do is we would need to lock both accounts A and B. And this is where we can have a potential deadlock situation. So the key idea is that whenever we are dealing with multiple locks, we may be looking at a potential deadlock situation. In such a deadlock situation, I mean, such deadlock situations are difficult to handle, but I'll provide a solution. So the deadlock is shown in the next slide. So let's assume that there are two threads A and B. So then thread A will acquire lock A and thread A will wait for thread B to relinquish lock B, right? And thread B will acquire lock B. It will wait on thread A to relinquish lock A. So as you can see, we have a circular wait here with no thread making any progress. And then what will happen is that we have a deadlock situation. So one easy way of actually solving this is known as two-phase locking. So what we do is that we impose an order on the locks. So we say that, look, you will first acquire, let's say, lock 1 and then lock 2, or first you will acquire lock A and then lock B. So then what will happen is that the moment you impose an order on the locks, then a deadlock is not possible, right? Because if you see, a cyclic wait is not possible. The reason being that we can always draw a kind of a dependencies, right? That I'm holding on to, let's say, one lock 1 and I'm interested in lock 2. Another thread is holding on to lock 2, it is interested in lock 3. So let's assume that the lock numbers also correspond to the order in which they are locked. So you will finally see that if I try to acquire the locks in a certain order, which in this case is 1, 2, 3, 4, 4 can never wait on lock 1, which basically means that after acquiring lock 4, I will never wait to acquire lock 1. The reason being that I'm acquiring locks in order. Given the fact that a circular wait is not possible, a deadlock is not possible. Otherwise, it is. So, of course, two-phase locking can be used to solve this issue. But here again, the assumption is that before a program starts to execute, I'm aware of all the locks that it will acquire, which in many cases, many times, I'm not. So this is where the modern paradigm of transactional memory comes into play. It's not really that modern. It was introduced roughly in the 2010 time frame. After that, there has been a lot of work. But fortunately, now we have a lot of sophisticated hardware and software solutions that implement transactional memory. So the two great plus points of transactional memory are that they provide disjoint access parallelism. They automatically manage the issue of locks and deadlocks and everything. So this entire lock and synchronization business is managed by transactional memory. So if I were to implement the same code using transactional memory, so the signature of the function would remain the same. The basic code would remain the same, but here is where the magic happens. I will just enclose the critical section within an atomic block, and the transactional memory subsystem would automatically do the rest. Right? So what would it do? It would automatically ensure that this piece of code executes in an atomic fashion. Furthermore, whatever locks need to be acquired are acquired. The programmer need not bother, and there will be no deadlocks. So all of this is being achieved by just wrapping this piece of code within an atomic block, as you can see, starting with the curly brackets here and ending with the curly brackets. So the atomic block implements a transaction. So in this lecture, we will talk about different kinds of transactional memories. They can be implemented either in software or in hardware. Let us now look at the properties of a transaction. So these are the same properties that are used in the world of databases, albeit they have been slightly modified to suit our requirements of transactional memory. So these are the famous ACID properties, right, which are extremely commonly used. They're extremely popular in the world of databases. So we have looked at atomicity earlier also. So in this case, of course, in the context of transactions, it varies slightly. So in the context of transactions, it basically means that either the entire transaction completes or fails, right? So which means that either it completes or aborts, right? So failing a transaction basically means abort, which means that the rest of the world either perceives that the set of instructions have either executed completely or they have not started at all. So it's kind of the same thing as what atomicity is in the case of reads and writes. So basically, we can kind of merge both by saying that the entire transaction appears to complete at some instant of time, right? So at some instant of time, it appears to complete instantaneously, or it appears to have not started at all. Consistency. So this is slightly different from a memory consistency model. But let's go through it. So a consistent state, as we have described before, is a valid state that is as per a given set of specifications. All right. So this is known as the consistency model, where we say that a consistent state is a state which follows a certain set of specifications, whatever it may be. It was the same case in memory consistency as well. The property of consistency in this case says that if the full system was consistent before a transaction started, it will also remain consistent after it ended, which basically means that, let's say, if the configuration of the entire system satisfied some property before a certain transaction started, when the transaction ends, it will still continue to satisfy the same property. Okay, so that is what consistency means in this case. Whereas in the case of memory consistency, it meant that at all points of time, the state is as per specifications. But in this case, it says that, look, the state is as per specifications, no doubt. And if we start at the beginning of a transaction, it needs to be consistent. And at the end also, it needs to appear to be consistent. Isolation, this basically means that while a transaction is executing, it appears that regular instructions or other transactions are not executing, which means that if a transaction is executing, it appears that the transaction is executing isolated. So it is not at all, its execution is not at all being affected by other instructions or other transactions, and it is also not affecting other instructions and other transactions. So one direct side effect of isolation is that, let's say, no other transaction or memory access can see an intermediate write of a transaction. So let's say the transaction is continuing and in the middle you write something, but you have still not committed the transaction. What does committing mean? Committing means you have not finished it. All right. So we will discuss more of this. But the key idea is that the group of instructions, the entire group as a whole has not finished. Right. So when it finishes successfully, you say that it has committed. So isolation basically means that in the middle of a transaction, nobody else can see any intermediate values, right? And finally, we come to durability. Durability says once a transaction is finished, its results are written to stable storage. This basically means that once a transaction has finished, its results cannot be erased. They are written into stable storage and they remain there. So a memory system that provides support for transactions is known as a transactional memory. And there are two types of transactional memory: hardware transaction memory and software transactional memory, as we have discussed. So hardware transactional memory provides transactional support in hardware, and a software transactional memory provides transactional support in software. So let us now look at the basics of transactional memory. So we have a read set and a write set for a transaction or a set of transactional statements. The read set basically says that the set of variables that are read by the transaction, that is the read set. Similarly, the write set is the set of variables that are written by the transaction, that is the write set. All right. So now let us introduce some terminology. So let the term Ri mean the read set of transaction I, Wi mean the write set of transaction I. Likewise is the case for transaction J, which is the read set and write sets are Rj and Wj respectively. When do two transactions conflict, right? So go back to our definition of disjoint access parallelism. and then try to come back. So they conflict only when there is an overlap in their memory footprints, right? If I were to formalize that, here is what it would mean. Either the write sets overlap in the sense the write to the same variable. If the write to the same variable, the intersection of the write sets will be non-null, then of course there is a conflict. Okay. So there is a conflict, no doubt, between them, because it's like a it's like a write after write or a var hazard. If there is a conflict between the read and write sets, which can happen in two ways, either wi intersection rj is non-null or ri intersection wj is non-null. In this case, what will happen is that the read and write sets will have a non-null intersection. And because they will have a non-null intersection, there is a conflict. Mainly because what will happen is that we can have a write after read or a read after write problem. Right, so this characterization is very similar to data races. So in data races, we had said that two accesses are conflicting if at least one of them is a write, which means that there has to be an ordering between them. So we can extend the same idea to transactions, where instead of single accesses, we'll be looking at sets. Right, so we'll be looking at read sets and write sets, as you can see over here. Right, that the read sets and write sets should not have an intersection. Of course, we are not considering one case, which is basically the intersection of the read sets of both the transactions. There is no problem as such if they intersect. The reason is that even in the case of data races, we did not have an issue, because if, let's say, two transactions read the same set of variables, then their ordering doesn't matter. There's no reason why the reads have to have an ordering that happens before ordering between them. Right? So the notion of conflicts between transactions directly extends what we have studied from data races. Now I'll explain two more basic ideas, abort and commit. They were referred to in our earlier discussion, albeit not defined formally. A commit is when a transaction completes without any conflicts. Conflicts means conflicting accesses, as described in the previous slide, which means it nicely completes and there are no write-write overlap problems or read-write overlap problems with other transactions. So then we say that this commits. Right? Other transactions mean other transactions which will ultimately commit. All right. So if there are no problems of this nature, then this happily commits. If there is a problem, which means a transaction could not complete due to conflicts, right? So what can happen? Well, what can happen is that if, let's say, you consider the same bank account example, where what we basically do is we first read in the value of the account into a temporary. We augment the temporary with the amount that is passed. Let's say that is in T2. And then we set the account's value to T1. If two transactions, two copies of this are running and the account is the same, basically what can happen is that we'll have two updates to account.val and there'll be no total ordering between them. So this will be a data race, no doubt. And also in terms of transactions, there will be a conflict because the write sets will overlap. So both the transactions clearly cannot commit, in the sense they cannot write the results to main memory or to the architectural state. So one of them has to kind of die and one of them has to be aborted. Aborted basically means that none of its writes or none of its changes will be visible. It will look as if the other transaction, the conflicting transaction, of course, if there are two transactions, T1 and T2, that are conflicting, then it is hard to say which one is conflicting, but let's say both are mutually conflicting. One of these has to be kind of scrapped, erased, aborted. So if T2 is aborted, it will appear as if T1 was the only transaction which was executing in isolation. And T2 never began, never executed, and of course never completed. So there will be no record of T2 or no record of any changes made by instructions within T2. So that is what abort means. Commit means successful completion. Abort means it will appear to the rest of the world. that you never started and you never did anything, even though you actually might have done something which led to a conflict, but all of that state will get erased. What happens after an abort? Well, the transaction needs to restart and re-execute. It's possible that it may abort again. So one good idea is that you might want to wait for a random duration of time to minimize future conflicts and then retry. So this is automatically handled by the transactional memory system. So what we can have is a do while loop where we will continue to retry transactions until the transaction commits. So tx.commit. So typically we use tx to represent a transaction in the transactional memory literature. So until the transaction commits, we continue to loop. Okay. And so we just continue to just loop, and loop, and until it commits. So of course, to reduce the probabilities of a conflict, we can do a random backoff. Random backoff means that we deliberately insert a sleep statement, let's say over here, where we just wait for a random amount of time and then again retry. Now let's look at the basics of concurrency control. Concurrency control basically refers to the subsystem that manages these transactions and takes care of, detects and takes care of conflicts if there is a need. So a conflict occurs when the read-write sets overlap. This we have seen. A conflict needs to be detected by the TM system. And a conflict is resolved when the TM system it can do two things. We have seen the second option, which is aborting a transaction. The other one could be that if, let's say, there is a write-write conflict, right? I'm writing to some address, let's say X, and then T2 is writing to some other, to the same address X, but the values are different. So what we can do is that if there is a conflict over here, we can, let's say, deliberately stall T2 and delay this instruction over here and just allow T1 to complete. After T1 completes, we can restart transaction T2 from this point. Right? I should rather add TX1 and TX2. So I should rather use this terminology. So what we can do is we can stall transaction 2 TX2 at this point, not allow the write to happen, so essentially stall the write. Once TX1 completes, we can release the write and then we can continue the transaction. In this case, at least there will be no conflicts because of this write. So even delaying a transaction to avoid conflicts, which means to deliberately avoid overlaps in the read-write sets, is also a valid technique. We can visualize this technique in a different manner. Assume that just before fetching the write instruction, because of some reason the transaction got stalled. So let's say the processor just went to sleep. Then the transactional memory would have never detected a conflict, right? And then the TM system, transactional memory system, would have happily allowed TX1 to complete. And later on, if TX2 would have woken up, it would have executed WX2. No conflict would have been detected, and then TX2 would have gone forward. So the delay mechanism is pretty much doing that. Whenever it sees a conflicting access, it just stalls a transaction until other conflicting transactions complete, and it restarts from there. So if you think about it, both the arguments are the same, and correctness is not hampered. So there are three aspects in any transactional memory system which deserve our attention. These are the occurrence of conflicts. So of course, this is an artifact of a program. Detection of a conflict. So there are many ways to detect conflicts, both in software as well as in hardware. And resolution of a conflict. Okay. So there has to be a means to resolve a conflict. All right. So that is the key idea, that we see a conflict happening, we need to detect and resolve. So there are two paradigms. The first is pessimistic concurrency control. So in pessimistic concurrency control, as soon as the conflict happens, we detect it and we try to resolve it. Resolve it could be either delaying the transaction or aborting the transaction. These are the two options that are available to us. But in pessimistic approaches, the moment that a conflict happens, we detect and resolve. In optimistic concurrency control, the moment a conflict occurs, okay, we don't do anything at that point of time. We wait till a later point of time. And at the later point of time, we detect and resolve. So this basically allows the system to continue despite the fact that a conflict has happened. We just safely allow the system to keep on executing it. We just allow the system to continue. And at a later point of time, we detect the conflict and resolve, right? So both have their own pluses and minuses. The pessimistic protocols are more overheads because we need to keep on detecting conflicts at every point of time, which adds to our overheads. And in optimistic concurrency control, we typically detect the conflict at the end, which is when we want to decide whether we'll commit or abort the full transaction. Now let's come to version management. So even in version management, we will discuss a lot more about version management. But here also, broadly speaking, there are two approaches, optimistic and pessimistic approaches. So we can either have eager version management or we can have lazy version management. So in eager version management, what happens? That we write directly to memory. Right? So any transaction which is executing, it just writes directly to memory. Okay. Nothing else. And then we maintain an undo log, which means that just in case the transaction gets aborted, whatever it wrote, it writes its write set. We just buffer the values that were overwritten for the first time. So that those are kept in an undo log. And once the transaction aborts, we take values from the undo log and repair the state. So what is it that we do? If we commit the transaction, then of course, since all the writes have been written to memory, nothing needs to be done. We just flush the undo log. But if we abort, so in this case, in the case of eager version management with an undo log, commits are fast. But if we abort for any reason, then there is a need to read in the undo log once again and write back the undo log to repair the state. So whatever may be written, since you want that none of the writes are visible, there is a need for state repair. Lazy version management. So for lazy version management, we write to a buffer, which is a redo log. In a sense, whenever we do our writes, we don't write it directly to memory, but so we don't directly write it to the memory system, but we write it to a separate region, which is known as a redo log. And once there is a commit, we transfer the contents of the redo log to the actual memory system. So the moment that there is a commit, we write back the redo. Okay. So far so good. That the moment that we commit a transaction, the redo log is written back to the memory system. However, in this case, aborts are fast. So in the case of lazy version management, aborts are fast. In the case of eager version management, commits are fast. So aborts are fast. So the thing is that since you have not written anything to the memory system, all that we need to do is we need to flush the redo log, and this we can do quite happily. So to summarize, there are two approaches. Either is that we are extremely optimistic and eager. So we directly write to memory, but we maintain an undo log, such that if there is an abort, the state can be fixed. Or we are kind of pessimistic. So we write to a redo log, and if the transaction commits later on, then the writes from the redo log are written to the memory system. So let us now come to conflict detection. So here also we can either be eager or lazy. So can look at eager. So as you can see the little bears on the right, we check for conflicts as soon as a transaction accesses a memory location. This does increase our overheads quite substantially, in a sense that accessing a memory location does increase our overheads because every single access now has to be burdened with checking for conflicts. So we can take a lazy approach if you look at the files over here. This checking is done at the time of committing a transaction. So let us look at the semantics of transactions. So we had discussed different consistency models when it came to regular memory accesses. So we have something quite similar in the case of transactions as well. So the metric that is commonly used is serializable. So this is also used in database transactions to a large extent. This is sequential consistency at the level of transactions. It basically means it is possible to arrange all the transactions in a single sequence where we are respecting the program order of transactions within each thread, right? So this is like SC at the level of transactions. We have strictly serializable. So if you would recall, in sequential consistency, we do not really care about any real-time ordering. So let me give you an example. Let's say that we set x equal to 1 in thread 1 and we set x equal to 2 in thread 2. So let's say the first write happens and then the second write happens 2 days later. Still in a sequential ordering, we could have the write that happened 2 days later appear first and then the write that happened 2 days earlier appear later. So sequential consistency will happily allow this. Absolutely no problem because the time at which an event actually happened doesn't matter, it's immaterial, right? And what really matters is whether program order is preserved or not and whether it is possible to arrange all the accesses in a single sequence which is legal. But strictly serializable adds a real-time constraint. So it makes the ordering consistent with real-time ordering, which basically means that if let's say there are two transactions that don't overlap in time, this means that transaction A starts after transaction B ends. Right, so after transaction B ends, if transaction A starts, it should be ordered after it in the equivalent sequential order. All right. So this basically means we look at all transactions. And let's say you consider each pair. In this case, as you are seeing, transaction A is starting at a point which is after the time at which transaction B ends. This means that in the sequential ordering, and mind you, these transactions are issued by different threads, not the same thread. So there is no program order between. Nonetheless, in the sequential ordering, final sequential ordering, A will have to appear after B. Of course, if they are concurrent in the sense if there is an overlap between them, then of course the ordering doesn't matter, right? So then the ordering is not specified. But otherwise, strict serializability, which is also known as linearizability, but I don't want to get into linearizability because that has a different definition and it technically is not meant for transactions. What is meant for transactions is strictly serializable, where we take the order into account. And the order basically says that if they are non-overlapping and one starts after the other, then the same needs to reflect in the equivalent sequential order. Now we'll come to opacity. Opacity is tricky. Opacity is tricky, but in a large number of cases, it's actually required. So we have only talked about committed transactions. We have not said anything at all about aborted transactions. Okay. So we have kind of remained mum about aborted transactions. So do aborted transactions need to see a consistent state, right? Which is produced. So a consistent state is a state that is produced by only committed transactions, right? So what kind of a state should an aborted transaction see? This means that an aborted transaction, is it allowed to see a state which is always consistent or can it be slightly different? And what implications would that have? So let us study this in the context of an example. So in atomicity, let's look at two atomic blocks. Sorry, not in atomicity, but to study opacity. Let's look at two atomic blocks. So initially, as is our convention, x is initialized to 0, y is initialized to 0. So that is our convention. So the second transaction sets both equal to 5, which means at the end of this, x is equal to y. And the first transaction does not read x and y, but it doesn't write to x and y, but it only reads their values. So what you would see is that in any execution where transactions commit, x will always be equal to y. Okay, if let's say these are the only transactions, x will always be equal to y. But let us assume optimistic concurrency control where we detect conflicts and also resolve them at the end. So assume thread 1 reads x as 0. Then the transaction on thread 2 finishes. So the transaction on thread 2 finishes, then clearly there is a conflict. But we at this point of time, we realize that we will abort the transaction that is going on thread 1 and we'll allow this transaction to commit. Then what will happen is that it will set x as 5 and y as 5 and x is equal to y. But look at what has happened. What has happened is that even though this transaction is going to abort, but since you're following an optimistic protocol, the commit abort decision will be made when we reach the end of the transaction. So the compiler will add some degree of extra code to make a decision at this point of time. But the problem that has been caused is basically that we have read x to be 0 and then this transaction has stalled. Now we finish the second one. Now we will read y to be 5. If we read y to be 5, if we look at this while loop over here, which will basically loop on while t1 is not equal to t2, we'll be stuck in the while loop. We will never reach the end. And given the fact that we'll never reach the end, we will never reach the point where we make a commit or abort decision. Since we'll never reach that point, our system is in jeopardy because one transaction has not aborted, but it'll just keep on running. It'll keep on using the resources of the CPU. It'll keep on running, and the system will be in an incorrect state. Right? So the system will be in an incorrect state. Why? Well, because this transaction is just continuing to run in an infinite loop and no decision is being taken on it. So if you think about it, why did this happen? This happened, so I'll just erase the ink. This basically happened because even though we were fully aware that this transaction is going to abort, we allowed it to read an inconsistent state. We allowed it to read Rx0 and Ry5, which can never be produced by a consistent state, which is defined as just the set of all committed transactions. That would never produce a result of this type because that will always produce a result which says x is equal to y. So in a sense, what has happened is that an aborted transaction has read an inconsistent state. So if we want aborted transactions to always read a consistent state, or I should add, even aborted transactions to always read a consistent state, which is produced only by committed transactions, we will have the property called opacity. Opacity will not allow y to be read as 5, so this problem with opacity will never happen, which basically means, if we go back over here, opacity means that even aborted transactions need to read or see a consistent state, which is only produced by committed transactions. Consequently, these two reads will not happen and you will not be stuck in this file. So of course, this was kind of a contrived, convoluted example, you may argue, but many such cases do arise in real life and many times arise inadvertently in real life. And that's why opacity kind of saves you. So especially when you're looking at optimistic concurrency, particularly with software transactional memory, opacity is definitely desired. Now let us look at mixed mode accesses, which look at both transactional accesses as well as non-transactional accesses. So a common correctness or consistency model is called single lock atomicity, where we assume that all the transactions are protected by a single lock So anytime a transaction begins, it acquires the lock and then it releases it. So of course, this lock is a hypothetical global lock, and data races are defined in a similar manner. But with this correctness model, or let's say this can also be a practical model if we decide to implement transactions in this manner, this will reduce concurrency big time, right? This will not allow disjoint access parallelism, not something that we want. So if we go back to our discussion on locks, we could use standard two-phase locking and have multiple locks. So this is called disjoint lock atomicity. So in this case, we use many locks, let's say one lock per variable, but the catch is that we need to a priori know which locks a transaction is going to use such that the locks can be acquired in a certain order, right? In a certain lock order, they can be acquired. So this aspect was discussed quite a bit in the previous slide, but this is one more model where transactions use multiple locks, let's say one per variable, but they acquire them in a certain order to avoid deadlocks. Then we have this model, transactional sequential consistency, where we basically assume that every non-transactional instruction is basically a single instruction transaction. So we can order all transactions, either committed or aborted, and regular instructions. Where, of course, what I'm not saying here is a regular instruction is being assumed to be a single instruction transaction in a sequential order. Everything, transactional, non-transactional, committed, aborted, doesn't matter. Everything can be arranged in a sequential order, which needless to say follows program order and is legal. So this is transactional sequential consistency. This of course gives us a lot. It's hard to enforce in practice. And as I said, all the instructions in the equivalent sequential order are in program order, including the ones which are within the transactions and transactions themselves, right? They are also in program order. So this is like the gold standard of transactional memory. So this is hard to implement in practice, but normally opacity is implemented. So now let's come to discussing practical protocols. So we'll discuss software transactional memory first. The choices that we have are a choice of the concurrency control mechanism, optimistic or pessimistic. A choice of the version management mechanism, lazy or eager. A choice of the conflict detection mechanism, lazy or eager. So what is the basic support that is required? The basic support that is required is that we augment every transactional object or every variable with some degree of metadata. This basically means that if there is some metadata associated with an object, we can keep track of its state and also use that metadata to detect conflicts. Along with detecting conflicts, we can also lock variables, and this can be used to stall other transactions. So we can also associate a lock with the metadata. So let us now see how we maintain read-write sets. Each transaction maintains a list of locations that it has read in the read set and written in the write set. Furthermore, since we are talking about software transactional memory, every memory read or write operation is augmented. So a read is augmented or it is replaced by a function. So the function in this case can be something of the form like readtx, which is basically you send the read operation to the memory and you enter the variable, the address of the variable in the read set. WriteTX is the same function analog for a write operation where you are sending the fact that you want to write, of course, the details of the variable. So that is implicit over here. And we enter the address in the write set if it's not already there. In addition, whatever changes are required to the undo or redo log, they are done. So all of this is done automatically within the transaction. The only thing that we do in the read The only argument that we actually send is the address, and the rest is all done internally. Similarly, the only arguments that are sent to the write_tx function by the program are basically the address that needs to be written and the value. So many times the programmer writes a normal program, but once it is enclosed in an atomic block, the compiler automatically converts it to a program that has these read_tx and write_tx functions within them. So what it does is that every access is replaced by a function call, right? And the function call is read_tx and write_tx. So we'll first talk about the Bartok STM, which is nice, easy, and simple. And the references to this you'll find in the book. So here we have eager version management, which means we have an undo log, and we have lazy conflict detection. So typically we do have lazy conflict detection in many software transactional memory proposals. So this should not come as a surprise. So every variable has the following fields. It has a value, it has a version, and it has a log. So this is what a transactional variable looks like. That along with the value, the extra fields are the version and the log. So this is what a read operation would look like. That when we read, we record the version of the variable. So we record, what is the version of the variable that we have read in our read set. We add the variable to the read set, and then we read the value. It's as simple as that. So reading in this case is an ultra fast operation, where all that we do is we just record the version, put the variable in the read set if required, and return. Writes in comparison are more elaborate. We will see why. So in this case, we first lock the variable. We will see why there is a need to lock it. We lock it at write time and release it at commit time. So we will see what is the need to actually do it. We add the old value to the undo log. Recall that we are using eager version management. So if let's say we are overwriting correct data, if we are overwriting data, then we add the old value to the undo log. But let's say there are two writes to the same address in a transaction. For the second write, this is not required. We write the new value. All right. Sorry. That's all. So the key point over here is that the write is made more elaborate because we are locking the variable, right? And it is also being made more elaborate if, let's say, we are writing to a variable for the first time in a transaction. So there is a need to update the undo log. So of course, if we are not able to find the log for a variable, then we abort. Now let's come to the all complex commit operation. So here what we do is that for each entry in the read set, we check if the version of the variable is still the same. So what you will see later on in the same slide is that after we commit, we increment the version of every variable. So this will basically tell us from the time that we read the variable till the commit point, has any write come in between or not. If a write has come in between, then of course there is a case for an abort. So this will easily be found out if we check the version of the variable. So recall that we are tying the value and the version of the variable together. And so then, so both are like part of the same package. So we just check the version of the variable and that's it. Say the versions are not the same, a write has come in the middle, so we straightforward, we abort. Otherwise, what we do is that the read check passes. So we move to the write check. And needless to say, since we are using an abort, the undo log has to be restored. So everything, all the writes of the undo log have to be written back. For each entry in the write set, what we do is that we increment the version and we release the log. Sorry. So for each entry of the write set, we increment the version and we release the log. So incrementing the version basically ensures, or it provides a signal to others that the value of the variable has changed. So just in case you read an older value, now you need to abort because the new value of the variable is what I'm writing to right now, and we release the lock. So the locking mechanism also ensures that the writes are mutually disjoint, the periods are disjoint. You can't write to the same variable by two threads at the same point of time because the second thread will never get the lock, right? And so given the fact that the second thread will never get the lock, you'll never have a write-write conflict. And the read-write conflicts can be detected by the version of the variable. So this is a simple idea. So the pros and cons are reads are simple, they are fast. It provides a strong semantics for transactions. But the negative aspect is that it does not provide opacity. Right? So opacity is something where an aborted transaction actually sees a consistent state. But this is not provided. And the other thing is that we are using locks, and also a lock is being held for a large duration. It is being held from the time of a write till a commit. You are kind of holding on to the lock, and writes themselves become slow because of this locking. Now, before you would ask the question, let me also say why it does not provide opacity. The reason is that if there is an aborted transaction, it will still, because we are using the undo lock based mechanism, its writes will still be visible in memory. So if you go back to the right slide, which is over here, you will see that its writes will be visible, right? So we are writing the new value that is directly going to memory. So of course, for a variety of reasons, we may decide to abort at commit time, but nonetheless, its writes will be visible. All right. So because its writes will be visible, an aborted transaction may not see a consistent state, and that will cause trouble. This is why this algorithm does not provide opacity. So with an undo log also, aborts become more expensive than commits, but if you expect a transaction to commit most of the time, aborts are not an issue. Furthermore, a transaction can read intermediate values which are written by other transactions. Hence, as we have argued in the previous slide, opacity is not guaranteed. And locks are also held and kept for a long time, so locking overhead is high. So now we will discuss the TL2 STM, which is slightly more sophisticated in the sense it does provide for opacity, and it uses a different method. Instead of eager version management, it uses lazy version management, which is a redo log. So one thing you can see quite quickly is that if, let's say, opacity is supposed to be provided at the software level, a redo log is required because that will ensure that writes are not visible. Writes will only be visible when a transaction commits, which means that any other transaction, be it aborted or committed, will always see a consistent state, and a state which has been created by committed transactions. But here again, there is a problem. It uses a global timestamp or a global clock, which needs to be accessed by all transactions. But a good aspect of this algorithm is that variables are locked only at commit time, and every transaction atomically does the following, right? At the time when it starts. So it increments the global clock. So both of them, these are atomic. So it's like a fetch and increment. Think of it this way. So in this case, it's more like an increment and fetch, but the idea being the same. So atomically it does both of these both of these operations, which are easily supported in hardware. The key point is it increments the global clock, and every transaction has a read version, a tx.rv, a read timestamp. So the read timestamp is set to the value of the incremented global clock. And since they are happening atomically, both of them together as a transaction. So of course, this is not a transaction in a transaction sense, but this is implemented using atomic instructions that we studied when we were discussing coherence. These operations can be done. And then the global clock is stored in the field tx.rv, read version. Now, what do we do when we are reading? Well, when we are reading of course, the transaction ID is important, and the object. Is the object there in the redo log? So the object in this case can be a memory variable as well. So if it is there in the redo log, we return the value from the redo log. If it is not there, then we do a little bit of a trick. So what we do is that we first read the timestamp. So here the timestamp is being used as the version. We read the timestamp into a temporary variable v1. We read the value of the object, and then we read the timestamp yet once again. And then we check if both the versions or the timestamps are the same or not. So why do we do that? The aim is to collect a snapshot, because you have a value and a timestamp, right? So what can happen is that you can read a value, and then, because of a race condition, the timestamp may change. Or you may read a timestamp, and because of a race condition, the associated value may change. So both may be out of sync. Because one thing you need to realize is that there can be an arbitrary delay between these instructions. So maybe we may read a very old timestamp, and then we may read the value, and then we may read another timestamp. So because of this arbitrary delay, what we should verify is whether the timestamps are the same. If they are the same, then we can be sure that this value corresponds to this timestamp. So this is a very standard programming idiom in concurrent systems where we actually read the timestamp twice, such that the value timestamp pair is collected atomically, where you know that, look, this value corresponds to this timestamp and this timestamp corresponds to this value. Fine, so we verify that, and we also verify, right? So in this case, to v1 should be equal to v2, otherwise we will abort. We also verify if v1, which now we have proven, which has to be equal to v2, if this is greater than the read version of the transaction, which basically means that some other transaction has written to this variable after this transaction started, so which makes the value stale. So if this is the case, that v1 is greater than tx.rv, then also we abort, which basically means a transaction started, but some other transaction has written to the variables after we started and it has committed also. So given the fact that the variables have become stale, we bail out, we abort. And of course, if the object is locked, then also we abort. All right, so we check for these three things. So this makes reads expensive. And then we add the read to the read set if this check succeeds, and we return the result. So the important points over here is this idea of checking the timestamp twice to ensure that the value and the timestamp are in sync, because otherwise we can have arbitrary delays between these statements, and the value and the timestamp may not be in sync, right? Because of the delays, you might read a value, but the timestamp may be for some other value. That's the reason you read twice and compare. And also to ensure that once a transaction begins, if any other transaction writes to the value after that, then there is an overlap. So we will have a read-write conflict. So this check over here eliminates the possibilities of this read-write conflict. Now let's look at the write operation. In this case, thankfully, the write operation is simple. We add the entry to the redo log if required, which means that if, let's say, this is the first write to that address, there is a need to add the entry to the redo log. Perform the write. Writes are cheap. Okay, so in writes, nothing need to be done. Writes are cheap, no problem. Coming to the all complex commit operation yet once again. So recall that in the Bartok STM, we were like heavily into verifying reads. But in this case, given the fact that we have made reads expensive, we actually do more with verifying writes. So for each entry in the write set, what do? We lock the object. So this is only a temporary locking for the period of the commit operations. In this case, we hold locks for a much smaller duration. So we lock the object. And of course, the locking is done in such a way to avoid deadlocks. In case there is a deadlock, it is detected. So the programmer need not bother. It is detected and recovery is initiated. So the programmer as such need not bother. But for each entry, we lock it. If it is a failure, we abort. Then what we do is that we increment the global clock yet once again atomically, and the incremented value becomes the write version. So we have two timestamps, RV and WV. So RV is read version, WV is write version. So for each entry in E in the read set, all right, so I'm sorry, this should be capital TX. So wherever, just have capital TX. So for each entry E in the read set, what do? We check if the timestamp is still greater than tx.rv. So this is the same check that we were doing over here. It is exactly the same check that we were doing over here. We were checking the version with tx.rv. So again, I'm sorry, all the time this should be, tx should be like this. Okay, so that correction will be made. But here the key idea is that we do this check once again, which means that at the time of committing also we are ensuring that there is no read-write conflict. Okay, the reasons remain the same. After that, what we do is that we write back the redo log, and for every entry in the write set, we increment its timestamp. How is that done? Well, the timestamp is set equal to the write counter over here, and we release the log. So this is all that needs to be done. So the commit operation is kind of similar, at least in principle, conceptually looks the same as the Bartok STM. But of course, in this case, we have a redo log. And the locking is for a much shorter duration. In the sense, we lock over here, we release over here. And of course, before we lock, in that case, we are incrementing the version. In this case, we increment the timestamp. And for reading, we just verify that there is no read-write conflict. Now, how do we verify if there is no write-write conflict? Well, that is quite simple. Given the fact that we are using a redo log, it could very well be possible that many other transactions are writing to the same write set, and there could be a write-write conflict. But in this case, keep in mind that for the entire duration of the commit, we are essentially locking the entire write set. If there is an overlap and we are trying to write at the same point of time, one of the lock operations will fail, and that's when one of the transactions will abort. If, let's say, two transactions with overlapping write sets are succeeding, it basically means that one transaction commits. So committing meaning at the beginning it locks a variable and then it releases. Then the second transaction commits. Lock and release. So in this case, as you can see, there is no problem even if the write sets do overlap. Because of a redo log, the writes are visible only after a successful commit. And furthermore, write sets can overlap, there is no issue, because the commits are still being arranged in sequential order. But if there is an overlap in terms of time, which is actually not allowed because that will become a concurrent and conflicting access, then the lock failure will indicate that two transactions are writing to the same lock, same object at the same point of time, and that would indicate that there is a need to abort. All right, so that is why a write-write conflict with a redo log is not a big deal. The read-write conflict is a bigger deal, but that we are solving using timestamps. Pros and cons, well, a simple idea, it does provide opacity. Well, why opacity? Because the moment we use a redo log, we only see the state provided by, created by committed transactions. We also hold logs for it's for a lesser amount of time. Of course, the redo log is slower, it makes commits slow. That's okay, we are getting a lot, we are getting opacity. So redo log, even though it's slower and commits are slower, that's okay. We still use locks, so we will try to remove locks when we go to hardware transactional memory. But in general, in software transactional memories, locks are required. So what is the settle point? Well, the settle point is we are using two timestamps per transaction, tx.rv and tx.wv. So we will have tx.wv is greater than equal to tx.rv plus 1. Right, so why greater than equal to? Well, it could be equal to if there is no transaction in the middle because there are two increments. Greater than it can be if other transactions have committed in the middle. So we first write the variables to permanent state, then we update their timestamps. This is typically what is done when you have a value timestamp combo. You first write the variables themselves to permanent state and then you update the timestamps. If another transaction sees an updated timestamp, it will automatically figure out that the value is there in permanent state. This justifies the order. And finally, we release the locks. So this allows later reads, all right, to go through. So this provides for opacity as well. So now we will discuss hardware transactional memory, as you can see. So hardware transactional memory's main advantage would be that it will not use locks. So let's now make a case for hardware. So STM systems do not handle non-transactional access. The reason being that these accesses are not instrumented. So we have not been replacing them with function calls. So that's the reason non-transactional accesses, even though they can cause a lot of trouble, data races and so on, but they are not handled. Acquiring, releasing, managing locks is quite expensive. Maintaining undo and redo locks, particularly in software, is also difficult. Hardware is much faster, but you have to create the hardware, which is is expensive, right? There are high startup costs. So the hardware support, which will be discussed, is mostly based on the widely popular LogTM proposal. You will find references for it in the book. So the basic ISA support that is needed is we need 3 new instructions for begin, abort, and commit. Version management, hardware schemes mostly use eager version management. They use the undo log. It is hard to maintain a redo log because you need a separate region and so on, but the undo log is the cache. Think of it, the basic L1 cache, L2 caches, they can be used as the undo log. And it's much easier to do so. We will see how. That's the reason eager version management is used. The log has its dedicated set of addresses in virtual memory. Right. So in this case, this is if we are using a redo log, that is. Otherwise, we just simply use the cache. So the cache line, every cache line is augmented with 2 bits, read and write. If r is equal to 1, this means that some 4-byte word out of this cache line has been read and it is a part of a transaction. So it is made a part of the read set. And if any word has been written to, then we set w equal to 1, which means that some word has been written to. So it is made a part of the write set. So here is the key idea. We make a small change to the regular directory-based cache coherence protocol to detect conflicts. So this is the hallmark of any of these transactional memory schemes, that instead of designing a new protocol, we use the regular cache coherence protocol to augment it to detect conflicts in the case of transactional memory. So let us say core D has a miss. It will send, so let's say core D has a miss, right? It will send a read miss to the directory. The directory will find that core C is a sharer, so it will forward the read miss to core C. Core C will detect a conflict. How will it do that? Well, it will try to read the line from its cache. It will find that it has written to it, which means it's a part of its write set. So it will see that there is a conflict. So it will send a NAT back to the directory. The NAT message will then be bounced from the directory. It will be sent to core D. Core D will realize that there is a conflict. So the transaction at D will abort. This can be done either in hardware or with some software support. So the support that is required is that the transaction, you have to clean up the state and retry. So typically a signal may be sent to software to retry the transaction. But the key point, the operative point here is that every cache line is being augmented with 2 bits, a read bit and a write bit, and they are indicating whether the line is in the read set or in the write set. But of course, what happens if the line gets evicted here, goes to L2 cache? Those are all corner cases. We'll gradually deal with them. So the key point, whenever the cache is being used as the undo log, is that if, let's say, the entire read and write set can be confined to the cache, then there is no problem. If it can be confined to the L1 cache, for example, then there is no problem, because if there is a commit, all that we need to do is that we need to set the read write bits to 00, which means they are not a part of a read write set anymore, because the transaction is committed. And there are mechanisms known as flash clear mechanisms, where basically what we do is that in the SRAM array, we have these read write sets as a separate sub array, and we set all of them together in one go. So descriptions are there in the book regarding how exactly this is done, and there are many patents as well. But the key idea is that this is a known mechanism. It's a simple mechanism of how you set a large number of bits to 0 in one go. If, of course, there is an abort, then also we need to do a flash clear. But there is a need to actually replace the undo log. To bring in the undo log and write it. So one small point is due over here. So when I meant that the log has its dedicated set of addresses, if you are using a redo log, for sure, yes. But even when you are using an undo log, the undo log has to be stored somewhere, right? So where will we store it? The undo log will be stored somewhere in a separate region in virtual memory, which will be accessible to the process and to the hardware. So if there is a need to undo, the hardware will automatically read all the variables from there and update the state, right? Such that the state is similar to what it was before the aborted transaction started. So fixing the state can be done by either software or by hardware. But the key point is that while a transaction is in execution, if there is an eviction, what happens? So if there is an eviction in the M state, the state at the directory is set to M at C, where C is the number of the core that evicted the block. For example, let's say if core 3 evicted the block, the state at the directory will be M at 3. M at 3 basically means it was there in the modified state in core 3, but core 3 evicted the block from L1 to, let's say, L2. We set the overflow bit of core 3 to 1. Okay. In the S state, let us assume that there are silent evictions, which means that in the underlying directory protocol also, if, let's say, there is an eviction in the S state, it doesn't necessarily inform the directory. So with that in mind, here is what we do. Whenever the directory gets a request for a block in the M at C state, so basically the state is, let's say, M at 3, and it gets a request from another core, let's say core 4. Then it will forward that request to core 3. So core 3 in this case, let's say, so in this case core 3, but we are calling it core C actually. So core C may not have the block in the cache. The reason being it may not have it in the L1 cache because it is displaced to L2. It will nonetheless infer a conflict because of the state of the block, because the directory is also sending its current state of the block along with the message. It will see that the directory's current state is M at C. Because it is M at C, it will infer that since the directory never lies, that most likely I had it in the modified state and I evicted it, and now somebody else wants to access it, but this block for sure is in my write set. So it will infer a conflict. So then what it will do is that it will need to do something. If it's a normal request, so the normal request will not have an M at C from the directory. I'm sorry, I slightly stand corrected. So if it gets a message with M at C, then it will assume that there is a conflict and it will send a NAK back, and the NAK will lead to an abort. But if it's a normal request, which means this M at C is not coming, then it will infer that the line was there in the S state, and from the S state it was evicted. So this is what it will infer. All right. And if the other transaction just wants to read, there is no problem. But if it wants to write, there is a read-write conflict. and a conflict has to be signaled. So in this case, what you see is you see a strange way of state management. So what is happening is that depending upon the message that is coming from the directory, say the directory is sending a message with an M at C to core C, it will figure out that, look, yes, I don't have the line currently with me in the L1 cache, but since the directory is sending this message, most likely I had it in the M state and it got evicted. And let's say if a request is still coming, it will then assume that most likely I had it in the S state and it got evicted. So let's look at an example over here. Core D starts the process. So the first thing is, of course, that so I'll start slightly from to the leftwards from t equal to 0. So the first is core C had a line, it evicted it, so it sent a message to the directory. The directory sets the state to M at C primarily because core C was the only code which had the block in the modified state. So it will set it to M at C, and then what it is going to do is that it'll not do anything. It'll wait for subsequent requests. When core D sends a read miss message to the directory, it will realize that its current state is M at C, so it will send the read miss message and the M at C directive. Core C will realize several things. It will realize that its overflow bit is set to 1 because this is set just after the evict. So overflow bit basically means that some line was in the read set or write set and it was evicted to the lower level, so its overflow bit is 1. If its overflow bit is 1 and the state that is coming has an M at C, then what will happen, right, is that it will automatically infer that there is a conflict. Because I had it in the modified state, I sent it down. That's okay, but it's still in my write set in the modified state, and somebody else wants to read it, so there is a conflict, so it will send a NAK back. The NAK will bounce from the directory, go to core D, and it will be a NAK, and core D will subsequently abort. That is the key broad idea over here, that core D will subsequently abort after it gets a NAK from core C via this mechanism. So this allows speculative data. So that's the term. Speculative data, because this data finds entries in read and write sets. It allows speculative data to be displaced from the higher level caches and sent to the lower level caches. There are of course some subtle issues. So assume a block has been evicted. If there is a conflicting request by a non-transactional access, then of course the current transaction has to abort because the non-transactional access cannot abort. If a transaction aborts, then of course you have to flush the read-write sets. So the read-write sets flushing basically means that all the R and W bits have to be set to 0. Right? All the R and W bits have to be set to 0, 0. In this case, what could have happened is some blocks might have been evicted and gone to the lower levels of the hierarchy. But since we restore the entire undo log, what will happen is that the correct state of all the blocks will get restored in the L1 cache. In this case, even if there are wrong values written by an aborted transaction and they are floating around in the lower levels of the cache hierarchy, it doesn't really matter. Because if you think of a processor, it only trusts all the data that is there in L1 cache. Something that is below L1 is assumed to be stale anyway, because L1 cache has the most up-to-date data. Say the undo log is directly written to the L1 level, can get evicted later, that doesn't matter. But if the undo log is written to the L1 level, then as far as the processor is concerned, the most up-to-date data is there, which is the undo log, which means any other value that was generated by the aborted transaction, even if it's floating around at lower levels, doesn't matter. After the transaction finishes, all the read-write bits with each line, all the overflow bits with the core and the M at C kind of bits, which C is the core number, all of these are cleared. Clearing these two is trivial, but we have already discussed how to clear these. And to clear these, well, there is something called a flash clear mechanism, which is explained in some detail in the book. Good. So now we have completed this huge, long, humongous chapter. So what we have seen is there are two broad paradigms in parallel programming: shared memory and message passing. Message passing is far more suitable for a loosely coupled multiprocessing system, but for any multi-core system, shared memory programming is used. Here, of course, there is a need to create specifications. So PLSC is something that all memory models follow and adhere to, and that lays the foundation for cache coherence. Memory consistency models are of many types. The key important variables are write atomicity and program order. These relationships are captured by the PO, RF, FR, and WS relations, which we have discussed in great depth. And to enforce the axioms of coherence, where the serialization axiom comes from PLSC and the write propagation axiom comes more from common sense that we don't want writes to be lost, there are many ways, many protocols, Snoopy protocols, directory protocols to enforce the axioms of coherence. And then we looked at data race freedom, and we defined what is a properly synchronized program. And if a program is data race free, its execution is in SC. Finally, we talked about transactional memory, its correctness properties, different protocols, hardware protocols, software protocols, and how easy it is to write correct data race free code, of course wrapped in atomic blocks and transactions, where the underlying system does the rest. So this concludes this chapter.